In our next chapter, we have quite a bit of review with a little bit of new material at the end. The topic deals with thermochemistry, chapter 6 in our text. Thermo, of course, giving us the idea that heat energy is involved through the course of a chemical change. I'll go ahead and turn into our first of the PowerPoint slides, asking you to follow along, taking notes if you'd like. We have forms of energy, and it's just giving us some examples here. Electrical energy is when kinetic energy is associated with the flow of electrical charge. As a matter of fact, in our last unit, we talked about electrical charge in terms of electrolytes. Those strong dissociated ionic compounds, commonly called salts, conduct a current when dissolved in water. Heat or thermal energy is when kinetic energy is associated with molecular motion. Molecular motion in gases is greater than those of liquids, and solids, of course, have the least molecular motion, very rigid in form. Light or radiant energy, when energy transitions in an atom, when an electron is either promoted or falls back into an energy level, light is given off. Of course, nuclear energy is when the nucleus of an atom actually explodes or comes apart to release the nuclear energy trapped inside. And chemical energy is that energy that's stored in chemical bonds as atoms are created into compounds. So it's an energy storage house, a potential energy due to the attraction of atoms as they create compounds. So just to clarify, if I take a simple example of a water molecule, this chemical bond, called a single covalent bond between the H and an O, truly is potential energy. It's energy being stored. And if I break bonds, energy is released, and as new bonds form, energy is being absorbed. So the breaking of bonds releases, adding bonds absorbs energy. We deal with the law of conservation of mass and the law of conservation of energy in chemistry. It simply says energy and mass cannot be created nor destroyed. It simply is changed from one form to another. So when energy is transferred between objects or converted from one form to another, the total amount of energy present must be the same from the beginning all the way to the end of the process. In this picture, you can see mechanical potential energy as this person is pushing down on a spring. Pushing down increases that potential energy. Releasing that creates kinetic energy, and yet the push down will equal the push up, being conserved. Here's some vocabulary terms. As a chemist, we think about the system as that part of the chemical reaction we are studying, and everything around that chemical reaction becomes the surroundings. The system is the bonds that are being broken and the new bonds that are being formed through the course of a chemical reaction. If we see that the system loses energy to the surroundings, we had a word to define that. It was called exothermic. If the system gains energy from the surroundings, we had a word for that, and it was called endothermic. It's keeping track, really, of the energy flow from the surroundings and the system. Comparing the amount of energy in the system and the surroundings during a transfer just lets us figure out if the system is gaining or losing energy, and yet realizing that the net change remains constant. The word conservation means to stay the same. If this is the amount of energy before the energy transfer, so the system energy gauge is about half full. If the surrounding energy gauge then is about a quarter full, a little less. Through the process of a chemical change, notice here the system lost energy, but notice an equal amount of energy was gained by the surroundings. The net lost by the system equals the net gained by the surroundings. Energy is conserved. The units of energy. Most commonly we use the metric unit known as the joule. Oftentimes, though, the joule is quite a small unit, so we often talk about kJs or kilojoules of energy. It's defined as the amount of energy needed to move 1 kilogram mass a distance of 1 meter. 1 joule is the same as 1 Newton meter, which is equal to 1 kilogram meter squared per second squared. Here in America, we often talk about calories of heat energy, especially in foods. It's the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. If you see a kilocalorie, commonly referred to as a capital C, that's also defined as 1,000 grams of water, which is 1 kilogram. So a kilocalorie raises 1,000 grams of water by 1 degree Celsius. Most common conversions that we will use, 1 calorie is 4.184 joules. 1 calorie with a C, notice that's 1,000 calories with a small c, is a kilocal, or 1,184 joules. And a kilowatt hour, most commonly used from a power source when the power company charges us for the use of electricity, comes in a kilowatt hour. 3.6 times 10 to the 6th units of joule energy. These conversions would be handy to have as you're tackling some homework where they're going to be asking you to convert from one unit to the other. So I'll keep my slide handy as well. This is a slide also that gives us an average energy use. If a joule is the amount of energy needed to raise 1 gram of water, 1 degree Celsius, we can see some equivalent values with the different units. The energy required for a light bulb, a 100-watt light bulb, to run for an hour, and you see the different values for the different units. An energy used to run 1 mile, again that's approximate, and the energy used by an average citizen in America. You can see the energy coming to us in the different units. This is a nice to know slide. When we think about the law of conservation of energy, we really are looking at Newton's first law of thermodynamics, the law of conservation of energy. And the study of that very topic is called thermodynamics. How do we change energy from one form to another and keep track of it as we do so? And remember, for a chemist, it's when bonds are breaking and new bonds are forming that we have a transfer of energy from the system to the surroundings. The total energy in the universe is constant, so we can never design a system that will continuously produce energy without some source of input. Alrighty. So energy flow and conservation of energy simply is taking a look at, again, if this is a gauge of the amount of energy the system begins with and the amount of energy a surroundings begins with. Take a look if the gauge is showing that the system lost, the surroundings gained. And we just simply talked that that was an equal amount, the net constant. I'll get the hang of switching this, I think. I'm turning them the opposite direction of what I need to. I apologize. So the term heat is the exchange of thermal energy from the systems to the surroundings. The system is the chemistry, the bonds that are involved in a chemical change, and the surroundings are us. And remember, that's where our thermometer is in our little calorimetry experiments. The thermometer is in the surroundings. Temperature is the measure of heat flow, and that's usually in a degree Celsius, although in the gas loss temperature we also